Okay guys, hello and welcome. Today we are going to be going through differentiation, okay, and specifically how to do differentiation by first principles. Now this is sort of going to be more like a revisiting video because a lot of people would have done differentiation but sort of forgotten how the formulas came to be. Okay, so what we're doing today is going to assume that you already have some knowledge on differentiation. What we are going to do is go back to the differentiation by first principles and try to understand where the formula came about. Okay, and if you're learning differentiation for the first time, this is also an opportunity to get used to that idea. Okay, so let's begin. Differentiation by first principles. Okay, so the reason why we want to do this topic again is because a lot of you may be using the formulas in differentiation, like the power rule, the chain rule, and not really understanding where it comes from and what the point of differentiation is. Okay, so we just quickly revisit the idea that differentiation finds the gradient of a curve at a particular point. The gradient of a curve at a particular point. Okay, and as we know, a curve will have changing gradients, unlike a straight line. Okay, so let's draw a curve here. So we know that, for example, the gradient here would be something like that. The gradient here may be something like that. Okay, so the gradient of the curve changes as we move across the x-axis and the y-axis. Okay, so we're going to see how we can use this idea to find the first principle differentiation formula. So let's start. So we want to find a formula for f dash of x, okay? So we want a formula for f dash of x, which you can recall is the derivative function, okay? Which is a function that tells us about the gradient of the original curve. So let's say we want to find, for any point xy on this curve, the gradient at this point. Okay, xy. Okay, and we'll say y is equal to f of x as well. Y is equal to f of x here. Well, this is, I'll label it here. Y equal f of x for any curve. So we want to find the gradient at this point. We're going to use differentiation by first principles to come up with a solution. Okay, first, we have to remember how can we approximate the gradient. So let's put this green line here. The green is the actual gradient. Okay, so this is the actual tangent, and we want to find the gradient of a line. We want to find this gradient. Okay, so we want to find the gradient of this line. Now, what we can do is approximate this gradient first, okay, by having a second point here, okay? So let's say that this point is at x, and because it's on the curve, we can simply substitute this point in and say f of x, okay? Well, this f of x means substitute x in, okay? Sub in x, okay? So let's call this a different one. Let's say we'll call this x1 subscript to show that it's a particular point of x, okay? Sub in x1 into the function. So maybe that makes a bit more sense. And here we'll take another point. Let's move across by h, okay? So we'll say that this point here is x1 plus h. So we will move along h to the right. And then how do we get the coordinate of this point here? Well, this point here will simply be x1 plus h, and then we sub x1 plus h into the function x1 plus h. Okay, so that's these 2 points. Now let's find the approximate gradient here. So how do we find the approximate gradient? We use rise over run. Okay, so let's let this red line be our approximate secant. So it's not a very good approximation, but it's sort of there, sort of pointing in the right direction, not 100%. That's okay for us. We can tweak the formula a little bit to make it better. Okay, so now, what is the gradient of this line? What is the gradient of this approximation? So to find the gradient of this approximation, we can just take rise over run. Okay, so let's change the color here. We can take the rise over the run. Okay, so this is the run and this is the rise. Okay, rise over run. That is going to be the gradient, because we have 2 points and we just want to find the gradient of between those 2 points. So this is something that you've done in year 8. But the only difference here is that for the values that we have, instead of having numbers like 2, 3, 4, 5, we will have these funny looking values, but the formula remains the same. We just have to use these formulas. Okay, so let's throw everything in. Okay, so the approximate gradient is okay, so we know that it's the rise over the run. So let's calculate what the rise is. So we want to see how much we went up, okay? And all we have to do now is to find the height difference between these 2 points. So how do we find the height difference between these 2 points? Well, we simply get the height of a taller one, which is going to be f of x1 plus h, and subtract that from the height of the smaller one, which is f of x1. Okay, so that's going to be f of x1 plus h minus f of x1. That is going to be the rise. Now let's get the run. So we use the same idea, and we can already see here that it's going to be h. Okay, so we know that this is the difference, h. Or we can say this is this one subtracted by this one. Okay, x1 plus h minus x1. So x1 plus h minus x1. Okay, so we can just simplify this to become just h. Okay, so this is looking a little bit familiar, right? But hold on, what about all the limit things that we were looking at before? Well, let's get to that. Okay, so to make this approximation better, okay, to get a better approximation, we want to get h as close to 0 as possible. Okay, and we can sort of imagine how that's going to work, right? So if I were to pick, say, this point instead, pick these 2 points, then our approximation, okay, this blue line, is going to get even closer to the green line, which is what we wanted to see, okay, versus the red line. It's a bit further away, okay? So the smaller h is, or the closer h is to 0, the better our answer is. But the problem is we can't make a direct calculation with h equals 0, because otherwise our gradient function wouldn't work. We'll have 0 in the denominator. So what we can do instead is take a limit, okay, which will allow us to examine the behavior of this gradient as h approaches 0. Okay, so to see what happens as h approaches 0, we take a limit. Okay, so let's take a limit. So if h approaches 0, then the approximate gradient becomes the actual gradient, which is what we want. So let's plug that into our formula. Okay, so to take the limit as h approaches 0, all we need to do is stick limit as h approaches 0 in front of everything. Okay, so let's do that. So the gradient of the curve at x equal to x1, which is like that particular point, then that becomes limit as h approaches 0 of f of x1 plus h minus f of x1 all over h. And that's our first principle formula, but almost. Now this is for, in this instance, what we've done is, here we have chosen any point x1, right? We've just chose any point x1 that's on the function. And because we have chosen any point x1 on the function, then this should work for any value, okay? This should work for, we'll say almost every value of x, okay? Almost every value of x. And the reason why I say almost is that there are, in circumstances where a particular point doesn't have a gradient, okay? For the example, at the bottom of an absolute value function, okay? At this point here, we cannot differentiate, not differentiable. But that's for another topic, okay? For now, we assume that the function is differentiable everywhere, okay? For now, don't worry. Assume it works for all x. Okay, so let's assume that it works for any value of x. Okay, so instead we can replace x with x1. Okay, so we can say, now let's call this new function f dash of x, which is the derivative function that we're looking for, and set it to be equal to this. Remember, this tells us, so we can plug in any value of x1 and we will get the gradient at that point. So plug in formula. So f dash of x is equal to limit as h approaches 0. Instead of doing x1, any particular point, we say just x, so any value of x, minus f of x on h. So this is the differentiation by first principles formula. Okay. Now, a lot of you may be wondering, okay, well, I've seen this formula, you know, we hardly ever use it because there are quicker ways to do it. What's the point of knowing all this that I've just told you? Well, it's really important to understand the concept behind differentiation. And that way you can apply it to the more challenging questions that will come up, especially if you're doing 4-unit or you want to get the challenge questions in 3-unit. Okay, so now that you know how this formula comes about, you can think about trying to understand where a lot of the other formulas come from. This is going to be really important to ensure that when you get to those challenge questions where you can't just apply a formula, you've really got to know how the formulas work to know which formula to apply in any particular circumstance. Okay. All right. So let's do a quick example. So just to refresh your memory on how to do these. Okay. So let f of x equal to x squared. Okay. Find f dash of x using that. Okay, so how do we do it? Let's just simply find everything that we have to and plug it in. Okay, so f dash of x, that's equal to limit as h approaches 0 of f of x plus h minus f of x on h. That's equal to limit as h approaches 0, and f of x plus h means we simply just substitute in this x plus h into x squared. So x plus h all squared minus x squared on h. That gives you, and we have to remember, we need to write the limit in front of each of these because we haven't evaluated this limit yet. Not evaluated yet. So we have to write it out in front of each step until we substitute in h, okay? But we can't sub in h yet, okay? Can't sub in h yet, since it is in the denominator. So we have to simplify a little bit before we can make that substitution. So let's do a limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, or 1h. The x squares cancel out, and one of the h's cancel out from each of these terms left. That gives you limit as h approaches 0 of 2x plus h. And now we can sub it in, okay? Now we can sub in h equals 0. So once we've subbed it in, then we don't have to write the limit thing at the front anymore. So that's just 2x, okay? So we have f of x equal to x squared, and f dash of x is equal to 2x. Okay, and that's also what we remember as well from the power rule, if we have learnt that yet. So we can drop the power in front and multiply it, okay? So the 2 goes to the front, and you subtract 1 from the power. So that's the other way we can do it. Okay, so that was just a quick introduction. Well, not really an introduction, but almost like a revisit of the differentiation by first principles formula to see how we got it and understand the background behind it, okay? So yeah. All right, thanks for watching, and I will see you guys in the next video.